All right, we're starting again.
Sorry, I didn't.
All right, close the door. Let's start again. Hello there. Okay, we are still in CPDs and TVs at an EIC, but we put nuclear PDFs in front now. So the first talk is about nCTEQ PDFs, improved PDF precision with EA measurements from Fred Olness. So same deal, 35 minutes and 10 minutes discussion.
Thank you. Pleasure to be here, and thank you for the invitation. Let me also start by thanking my collaborators on CTEQ and CTEQ NXFitter. And what I'd like to tell you about today are some of the things we've been working at. And I'll tell you a little bit of the dirty laundry about some of the things that we're struggling with behind the scenes. And in particular, I think these are some places where, as we work toward EIC, we can prove that, of course, the EIC data. And then at the end, we've got some shiny new toys or playthings in your perspective that I'd like to tell you about very briefly. So with the PDFs, there's a lot that is going on in there. It's a very complicated, strongly interacting system, but of course, we're going to model that very simply, as I say here, in the limit of a spherical horse, and that's for the proton. And the challenge is we try to get higher and higher precision. We just heard about the NW limits coming out of the LHC. As we try to get higher and higher precision, all these things that we're neglecting previously come around to catch you. And then you have to, as you push the precision up, you've got to pay attention to these things more and more. And that's certainly true. We've realized that in the proton case, now that the standard for the proton is next leading order. For the nuclear case, we're only working in next leading order. But again, all these issues that we sort of sweep under the rug or approximate or just sidestep come back to bite you as you try to increase the precision. And I think this is a place where the EIC can really contribute. And so to start with, coming from the high energy side of things, when I address my high energy colleagues on why we're interested in nuclear PDFs, I always have to remind them that they're actually essential for the proton PDFs. Some time ago, back during the area of Tevatron HERA, there was a group that said, well, let's just take proton-only data. We have HERA, we have Tevatron, that's all we'll need. We'll get proton PDFs. We never have to touch nuclear PDFs. You probably haven't heard about that because that didn't work so well. And in fact, it doesn't work so well even today because one of the key ingredients of the proton PDFs comes from, for example, neutrino deep inelastic scouting on nuclei, because you've got the 4 linear combinations of the flavor combinations. So that's really essential. And there was a study done by the NNPDF group just recently. If you go and take out all the nuclear data, including the deuteron data, that the degradation in the central value is more than a sigma. So this bar here is about a sigma, both in the central value and about half a sigma in uncertainty. So you really need it in there. You need it in there, but of course the nuclear corrections that we don't understand so well come back and introduce themselves in the uncertainty. And as we try to press for higher and higher precision, this is going to be a challenge. So let me introduce you very briefly to the players and the ingredients. And essentially there are 4 nuclear PDF sets currently. The original one, Kamano and Company, was the first one doing the evolution to next leading order analysis. And then there's EPS09, which has been superseded by an updated set 16, which includes both LHC data and also the neutrino data in it. And then the older DeFlorian set and the nCTEQ 15. And actually, there's a new group on the horizon. There's a recent effort by the NNPDF group to also include nuclear PDFs. And this, they're just starting here, but this could be quite interesting In particular, for example, with respect to the protons, when this is an older set in a PDF 2.0, but when you're looking at the strange quark distribution uncertainty with the proton PDF, what you see here is I've got nCTEQ and MSTW, and both of those, if you go down to small x, it's really sort of extrapolation. The parameterization ties your hands. You really have one parameter, it's x to the a, that's determining small x behavior. And so when the data runs out, what goes beyond that is pure extrapolation, whereas with the no parameterization neural net PDF, you really see when the data runs out, it starts to enlarge. So it could be very interesting. It's also very interesting to have somebody coming in from an orthogonal point of view. But then, of course, the challenge is because we have so little comparative data on the nuclear set compared to the proton set, whether there will be enough to get a meaningful result out of this. But that's just starting, and so look for that. It'll be interesting to see how that develops. So the ingredients with the nCTEQ 15, we're dealing with 19 nuclei spread all the way up to lead. And so this is a nice set, but again, compared to the proton set, we've got about a little under 1,000 data points, and most of the others have that. But that's to do all the way out to lead. In contrast, the proton sets have about 3 or 4 times that number. And as a result, the uncertainties on the nuclear compared to the proton are much larger. So this inner band is the proton, the outer band is the nuclear, and again, probably a small x, that's an underestimate coming from parameterization limitations. But nevertheless, this is what we do. And again, you know, the EIC can fill in some of the A information. I actually went back and made this based on a question I got by Rolf a while back. So here it is on the ZN plot. And so we've got 19 points. We're sort of going along the line of stability here and parameterizing things in terms of A. So the proton in a nucleon A, it's parameterized with this A combination. And then to get the actual nuclear combination, we take that, Z of that, and then use isospin to get that to actually build up the full nuclear structure. So it's an approximation we're working on here. I mean, at some point it was interesting on Monday, Baron showed, you know, working with the equal mass isotopes. That was quite interesting. But this dimension we can't describe. But this is, with the inputs that we have, the best we can do. And of course, what we'd like to do is fill this out a little bit because, again, we've got 19 points extrapolating all the way out to 208. So there's quite a bit of space here to fill in a little bit. Now, as I said, to build up, to go from the proton to build up the actual nuclear, we use isospin symmetry, and we get by with that at next leading order. But if we go to next leading order, then of course, at that point, just count on your fingers, alpha S squared is order alpha vector weak, and maybe you should put the photon in there, which is going to spoil your isospin symmetry. So again, isospin symmetry is in there. At the level we're working now, we don't have to do it, but again, as we push to higher and higher precision, we won't be able to do this, and we're going to have to account for this at some point. Now, in the proton case, they have this in there, they have sets with this in here, and you can look at what it is. You know, there are ways of handling that. We're not there yet, but again, we will eventually. Again, we can learn from the proton analyses how to handle things like that. So the data sets that go in here are typically, it's the deep inelastic scattering, the Drell-Yan, the neutrinos I put separately. I'll talk about that in a minute. And then the pion production from Rick, for example, is quite useful in trying to get some information on the gluon. And then these are the data sets. So as I said, nCTEQ 15, we have about 740. Most of these have around 1,000, except for EPPS 16, which included the neutrino deep inelastic scattering. And there, the nuclear correction is somewhat uncertain, but so that's the reason for the increase. And then typically we put cuts on Q and Y. So these are the cuts in the nCTEQ set. So there's a Q cut, so we cut out all this low Q data because you know, we're afraid to try to work in that region. We also use a W cut that cuts out the higher twist, high Y region. So we leave a lot of data on that's cut onto the floor, and it would be interesting to sort of press in this direction. So if we try to press in the low Q direction, for example, I show this. This is the bonus data sort of extrapolating down into the resonance region. And if we can press down there and have better description of that so we can integrate that, that would be quite interesting. And I like this sort of transition. I borrowed this from Rick, showing sort of the transition to the perturbative region and the non-perturbative region. It's a nice thing to do. And it's a little bit like we're looking under the street light because that's where the light is. But if we can describe these better, the higher twists and things like this, maybe we can go down and not throw away all that very interesting data and get collective effects like this. So I say the EIC can push these boundaries, but that's going to take both some theoretical guidance and some experimental guidance. On the high X side, there's actually quite a bit of recent work that's been going on there. In particular, the nCTEQ JLab effort has been looking at that. And they've been going, pushing up the high X, including, here's just an assessment of if you include the various data sets, how you can trim down the uncertainties on the high X region. And it sounds trivial, but in fact, one very important ingredient here is just the parameterization of things like the D and U bar distribution, so that as you go to X equals 1, you can get something besides 0 and infinity, which most of the parameterizations do. So they have a generalized parameterization to handle this. And of course, as you go to the limit of X equals 1, depending on various models, you expect various things. And so now that you can model this more sensibly in your PDF, you can actually start testing for this. And they've done quite a bit of measurements there. Let me also come back to the PDF parameterization. And so again, the way the parameterization is done, for example, the way the other groups do it, they use a multiplicative factor. They take the free proton PDF and they have a multiplicative factor given to the nuclear PDF. And for example, the EPPS uses a piecewise. They break up the correction into 3 pieces and set that up and multiply it. And these X1 and X2 breaks are, these X breaks are actually determined. That's a bit of a challenge, particularly in some of the more complicated regions. It's difficult to get a result for that and to get the shape. And then, of course, the EM, this sort of characteristic EM shape is built into it. In contrast, what nCTEQ does is we have we take the proton parameterization, sort of a generic X to the C1, X1 minus X to the C2, and we just make that we generalize that, make that A dependent. And when we do that, we add 3 arbitrary coefficients. Here's C0, 1, 2. And this is set up so that basically this is the proton. So when A goes to 1, this drops out. And this is the proton. That means we can use the proton as a boundary condition. And so it's normalized to basically a variation of essentially nCTEQ 6.1. And so the nuclear sets have 3 times as many parameters as the proton set. But if we use the proton to nail this down, we're down to only 2 times as many. But of course, since we don't have as much information, what we have to do is where the proton sets now are typically using to the order of 30 degrees of freedom, we're using typically 16 degrees of freedom, so we've got to impose some symmetry, some constraints, and things like this. So that's what we do, and then given that, we can then just do the individual evolutions, and here are the 19 nuclear PDF sets that we get out. So even though we use very complementary parameterizations, it's reassuring to see at the end of the day that the central values and uncertainties are relatively comparable. So here are the 4 sets shown for the gluon and the strange, and there's general overlaps there. So it's good that nothing drastically seems to be dependent on this. But again, to sort of drag out a little bit of the dirty laundry to a place where we want to improve a little bit, if I look at the individual coefficients and see how they evolve in A, for example, they're in the full parameterization, we actually have 5 terms. Each of these are A dependent. So here's a plot of those versus A. In the case of the gluon, they sort of move quite smoothly. That's reassuring. But as you go from proton to lead, things are okay. But for the case of the up valence, where a couple of them are fairly smooth, there are a couple that vary quite a bit. And so here, going from proton to even deuteron, we get a large change. And that suggests that maybe the way we're parameterizing this down here isn't the best, and maybe some of the changes, even that low A region, we have to go back and look at a little more closely. So, this was a great start. This is our first attempt at that, but we may have to, to get higher precision, look at that a little bit more.
And if you go back to the previous slide, my worry is always, and you see it a little bit over here, the way EPS and HKN and yada yada do it. In the end, your nuclear gluons are going to get a memory of all of these nuclear corrections they stuff in, and the gluons might not see this at all.
Yeah.
So you see it always if you look at the nuclear ratio of EPS and HKN, that you kind of get this EMC shape back, but it's really not based on data. It's partly the parameterization.
It's partly the parameterization, and then for nCTEQ, there's nothing put in, but when we look at ratios, they're comparable. Again, as the airs go down, then you may start to see.
But you don't have in your plume ratio. You don't have, I think, that shape.
We don't force the shape.
Yeah, exactly. And they have the shape still back. You see it. So
right. EPS, HKN doesn't.
EPS still has it. Right. So there is an extra model dependence in there in that sense.
Yeah.
So can I ask a very naive question? So if I guess those coefficients CK1, CK2, etc., are they mainly positive or they mainly negative? Because if I look at your plot, sorry, if you could just go back to where the coefficients were.
You want the formula?
Yeah, I wanted the plot there. So it seems like the larger the nucleus, the growth of small x gets slower for larger nuclei.
As you, so this is a deuteron,
Right.
and oops, did I have that?
No, that's right. That's the shadowing.
Yeah. Right. So
that's just shadowing.
Right. So some sort of shadowing or even in a linear. Okay, but I guess if I look at the formula, the larger the A, the larger is the factor multiplying CK1. Does it mean that the steeper is the power of x?
it's well, yeah. Then you have to fold. I mean, there are 5 of these. They're a full representation. Yeah, so it's not quite so.
Okay.
Yeah, it's not quite so obvious from there.
But overall, the qualitative behavior is the larger the nucleus, the more shadowing you get.
I mean, that's coming from the field, right? If you set 3 parameters, that could be positive.
But that's what I'm asking, right? I'm not asking what they could do by hand, but what the data require.
Yeah, that's right.
So very briefly, we've heard a lot of generalized PDFs before, and I guess there's some afterwards, that I found that very instructive and learned quite a bit. And so again, on the PDF side, this really serves as a boundary condition. And so, let's see, Ray showed this, but here's the normal PDF, and then the relationship between those. So it's sort of interesting that this meaning fact, here's some of the relationships and what's being done there. And again, I think both ways, communication, so mapping the TMDs, for example, back onto this, if we can get information here, or vice versa, back and forth. It was interesting in the previous talk here when they swapped the proton PDFs, how that changed things. And so I think some of that communication, again, going both ways, could be quite useful. But let me pull up some ancient history, and this is an old paper by John Collins and Keith Ellis going way back. And what they were considering was they were doing drawing-in production of W and Z. And at leading order, you've got collinear partons coming in, and they produce the W and Z, and it has 0 PT. And that means if you're interested in the transverse momentum distribution, which Fergal was measuring, that you have to do a next leading order calculation to get even a leading order estimate of the transverse momentum. And so what they propose is to basically include or absorb, put in a transverse momentum into the PDFs and use transverse momentum PDFs. And then at leading order, you had a finite transverse momentum. And basically, it's a reorganization of your perturbation theory. But what it means is you can then, doing a leading order calculation, you get a leading order estimate of the transverse momentum, and you're not sort of penalized order by order.
Right, that I should mention that there was a simultaneous paper by Francesco and
It was about the same time? Okay, yeah. So, but anyway, again, that's sort of ancient history, but let me rewind to more recently, and actually John, along with Ted, who's now at JLab neighborhood has this paper, and I have to fully absorb it, but it's sort of nice that they connect up, as we've seen here, the CSS to the soft collinear to the DMD. And so again, this gives us a framework to work from, and then going back and forth, projecting the TNDs on PDFs or vice versa, using that as the base could be quite interesting. So I think that's a new and interesting thing. I don't know much about it, but I've learned a lot here, and I'd like to continue exploring that. So yeah, I think that'll be an interesting avenue. Very briefly, we mentioned the strange PDF. And here, this is something where the neutrino deep inelastic scattering nucleon comes in, because this is the best way to measure it. But of course, that brings in the nuclear corrections, which seem to have a uncertainty here. The red line is what seems to be preferred for the neutrino DIS with the charge current exchange, and the blue curve is from the charge lepton with the neutral current exchange. And so what's the right nuclear correction? And I think that's still out. And unfortunately, there's no data on the horizon that's going to resolve that. So you've got quite a discrepancy between the two. And of course, if you're trying to get the strange quark out of there, again, at a crude level, you can do that, but if you want precision, then these sort of differences are going to come in. And then there was some thought that, well, gee, go to high energy, go to the LHC, it'll all be solved. But in fact, they have their own strange crisis. This is the Atlas extraction using inclusive W and Z, and they get a strange fraction of over 1 compared to the D bar, which is sort of surprising. You can see here the original PDF estimates. So again, high energy doesn't necessarily help you, but this is some place where the EIC can help. And they pulled this. This is LP showed this at the users group meeting. In fact, doing a reweighting with the NNPDF, that you can actually get quite a bit of information, particularly in this region. So that will help out quite a bit. So we'll look forward to that. Very briefly on heavy quarks, moving strange to things a little bit heavier. There are lots of potential issues that come in here, and they're interesting because you've got a multi-scale problem. You've got a mass. So whether you're talking about the charm at the bottom, you've got a new mass that gives you new logs to deal with, and the Higgs is proportional to mass, so that comes in there. And there are many issues. Let me just talk about one. And this was actually a study done at the INT for the, I think, one of the older EIC studies, looking at the intrinsic charm distribution. And so this was using the nCTEQ 6.6, and then you put onto it a charm component with either a 1 or 3 pair cent momentum fraction. And so that was actually quite visible if you look at do the DIS studies and do the angular distributions. That came out quite a bit. And it was interesting because then a few years later, we had this anomaly in the at D0, the photon charm final state, where the data was riding high in the largest PT bin compared to the theory prediction. And although there were a number of explanations, it was sort of curious that an intrinsic charm had exactly that type of behavior. It kicks up the highest PT bin, but didn't modify the lower PT bins. So far, there doesn't seem to be any evidence for that at the LHC, although you can look at, say, who on strange goes to CW at the LHC, and that's one of the ones that they use to cross-check the S distribution, the inclusive S distribution in Atlas. And at present, there's sort of tension between the CMS result, which uses this to get it at the strange distribution, and the Atlas inclusive WZ. So again, as the precision goes down, we'll look to see how that holds up, and it'll be interesting to sort of pursue that. Let me switch in the last bit of this to some of the tools and some of the things we've been working on. I just want to flash some of the nCTEQ developments and then Xfiter in the PDF sense. So nCTEQ, we've taken this code, and this grew out of some of the CTEQ work that was originally done in Fortran. And in the nCTEQ Fortran dealt with just the proton, and then we added the nuclear dimension, and so Ingo Schieblein led that effort, and that was all built up with Fortran. But then we had a number of some of the younger postdocs come in, and they said they refused to do Windows or Fortran, so we've converted that to C++, and I have to confess, they dragged me kicking and screaming, but I'm coming around. And in the process of rewriting that, we made it more modular so we can plug in modules. Now, MIDI we had used before, but that's now a plug-in module. And Hoppit, instead of an internal code that we wrote, we used Hoppit, actually a modified version, so it could deal with multiple grids at the same time. That's how we handle the multiple nuclei. But along with it, we added modules for the MCFM program in AppleGrid. And so this is the very structure, I should say. These are the postdocs and others who contributed to that. But one of the things we can do with that is, for example, studying the W and Z production. Previously, what we did was we used the Fuse program, and to do proton lead, Fuse is set up for PP, so it can't do PA. So we hacked the code. That took a month or two to hack and a month or two to validate. And then we got that working. And then you run it for about a week or so and you get a comparison. And that was very nice for a post-fit comparison. But you can't put that in your MIDI loop. You just could never make it. So what we did was we took this, validated it in the PP mode to make sure everything's working right, and then validated against the MCFM PPWZ production. And then MCFM is able to put out Apple grids. And so we put out Apple grids somewhere between 10 or 15 separate Apple grids. And what's nice about this, if you have enough statistics in the Apple grids, it actually becomes independent of the initial PDF. And then you can combine those with the statistics. And then when you're done, you have a PDF independent Apple grid. So this, with the Fuse method, you run for a week and get a result. In this case, you run for a week to get the Apple grid, but once you have the Apple grid, then it's a millisecond to actually do the final convolution, just to sum over the grid. And so you can now put this inside your grid. And even more, even though we generated this for the PP case, because it's truly independent of the PDF, we can use it for the nuclear PDF case. And let me just show you the validation of that. So this is the red curve. The red histogram is Fuse. We're looking at W plus productions, CMS data here. But the red histogram is the Fuse one, and that represents about a week of CPU. And the blue curve is the Apple grid. That represents about a week of CPU to generate the grids, but then about a millisecond to do the final convolution. And within the numerical accuracy, that does quite well. And so now with this tool, instead of doing the comparison post-fit, we can actually put that into the fit and do it. And it works not only for proton-proton, but it works for the nuclear case also. Now, we spent a lot of time and got this going. This is great. We have WZ in there. But even better, now that we have the framework with these plug-in modules, MCFM has about 1,000 processes in its library. So we're using the first two right here. But now that this is incorporated, in principle, we can do the same for any of these processes here that are implemented, and then just go ahead and do that. So again, this is, as I said, this is our shiny new tool, and it works, and the fit with the W data is ongoing. Hopefully, we'll have that maybe next fall if there's another meeting, we can present that. But that's going in. And because the initial chi-squares are actually quite large, it has quite a bit of pull in the nuclear PDFs. So I think it's an important computational device, and it gives us, for us, it opens up a lot of possibilities into many new processes. And previously we had deep elastic Brilliant jets was the main input. And now we have the ability to put in processes much more quickly, and it doesn't take months and months of rewriting the code. So this is quite an advance, and I have to say I acknowledge the postdocs that did it. As I said, they dragged me kicking and screaming into C++ and Python, but I'm warming up to it.
Can I ask you, in this respect, does it help, say for instance, if you differential distribution. Say instead of the mass distribution, you want a double differential, triple differential. Is there an advantage in this tool or not so much?
In principle, there is. We had to try that. And when I'm sidestepping here, I haven't shown it, but in the WZ data, we're mainly looking at rapidity, because as we were just talking about over the coffee break, the PT, you have to do the resummation, and that's more complicated. So what we've looked at so far, we've focused mainly on rapidity, in part because the PT you have to do the resummation. But now that that's in there, in principle, we can generate the grid for the PT. It will use whatever model is in MCFM. So, there are various things, various coefficient choices. In principle, it'll do that, but it's only as good as what's in MCFM. So.
Are you also including the GS from there to see? I know GS from Paraton.
Yeah, we have not. Actually, EPS has they have a grid technique to put the jets in, and they put the single jet.
And there, the current issue is that what kind of accuracy you want there. There's recent calculating for next video or jet per second.
Yeah.
Quite sizable correction. So that will affect the ground distribution.
Right.
I don't know.
Right. Well, as I said, generally we're using next to leading order because that's sufficient for given our error bars. But if there's especially large correction next to next leading order, then and again with this machinery with modular framework, we're linking a hopping. So I can flip a switch, I can do NNO evolution. It may not mean anything, but I can do it. And so in principle, but the pieces are there. So. So on XFitter, I want to say a few things about that, because actually this is a open source tool that can be downloaded and used, and I encourage you to do it. The current version is 2.0, codenamed Frozen Frog. I'm not quite sure the history of there. I'm sure there's an interesting one. But it's actually quite versatile. It's got DIS, JETS, Drell-Yan, can do diffraction top, WZ, and it's plugged in. For example, in particular, it's got a variety of heavy Quarks schemes, so you can do all those comparisons. Let me just very quickly flash some possible uses of it. So here it has TMDs. This is a modulant implemented by Hannes with, so just a sample of that with experimental uncertainties. It also has the ability to vary the heavy flavor threshold. This is a fairly new addition, and Valerio Bertoni did that. And then, although it cannot do multiple nuclei at once, it can do protons, but it also can do a single nuclei. So in this case, if I put in lead data and ask it to do profiling, it can do a profiling and say how much will this data shift the PDF, so we can use it like that. And there is an attempt, a Tübingen group is looking into extending this to two nuclear PDFs, multiple ones. So that is in progress. And also fairly recently, it's been extended. They have a student working on doing this for High Can PDFs. So that's coming along there. It's open source, so if there's something you would like to see and would like to plug it in, I encourage you to get involved. So it's quite useful. This is used for a lot of the PDF analyses at OSC, but again, if we extend this in the nuclear direction, then in principle could be an open source program resource for the IC also. And then very briefly, just one other recent tool. This is things that we've been doing at SMU. Pavel Nadolsky has been leading that effort, along with Tim Hobbs and company, is the PDF sense effort. And basically, you take the correlation, which is quite useful, but it does include the pull of the experiment to it. So you take the correlation, basically weight that by the residual, that is a shift of the data scaled by some measure in some sense. And then what you can do is you can look across the XQ plane and say, where does the impact come? And so I'll just show you one example. This is that sensitivity on some scale for the up quark. And this, we're using JLab EIC pseudodata and LHEC pseudodata. And so what you can see here, for example, on the sensitivity scale going from low as green, red as high, you can see in particular the JLab EIC has some particular sensitivity up here at high X, also down here at low Q, and then here's the LHEC, again with very good sensitivity down in low X region. And so you can look at the various impacts of this, and it gives you a fairly quick way of what you can say and how different data will impact the fit without having to do a full fit. And now that, again, the CT set is up to 4,000 or 5,000 data points, so a full fit takes quite a bit of time, whereas this runs on a laptop quite quickly. You can do these sort of assessments and do it quite neat. There's a link here to some to the data. You can actually download and try this. And again, when you have the sensitivity information, you can take this and you can throw some artificial intelligence tools at it. And this is something we're just starting on, but I thought this particular result was quite interesting. This uses the projector tool of Google TensorFlow. And what we did, we took the 4,000 points ago in the nCTEQ fit, and we just gave the residuals. So we have 28 variables, 56 error eigenvectors. And so for each point, you get a 56-dimensional vector that basically gives you the pull with respect to those eigenvectors. You take that 56-dimensional vector, throw it in here, and it reduces it down to a 10-dimensional principal axis form, and then you can project any three of these. And then we've color-coded the points for DIS, Brilliant, and JETS. Google doesn't know where the points came from, but it sorts these in a particular way based on the residuals, and you can see it sort of groups the colors together. And so somehow, based on the residuals, it's figuring out that these are associated, these have commonalities, and things like this. And so this is sort of new, fun, it makes pretty pictures. We're thinking about how to use this a little bit. And actually, there's a recent preprint that has some animations that are rather interesting. But using these tools could, it'll be interesting to see if this can give us some hints about ways to combine variables or combine things to see if we can get more sensitivity in some things. So that's just sort of a stretch type experiment, but I thought it was sort of interesting. So anyway, I'll go ahead and finish up there. First, again, let me thank my collaborators. This is some of the nCTEQ people hard at work you see. And then this is the XFitter folks at the recent workshop. And so again, I've sort of, hopefully, as I said, shown you a little bit of the dirty laundry, some of the things that go into the PDFs, and there's quite a bit of place where we can improve, particularly with the nuclear case. We can learn a lot from the proton situation, but again, just the lack of data, we have a lot to do, in particular the low Q and the high X has lots of opportunities. And then as we get the uncertainties down lower and lower, we're going to have to deal with these. And a lot of these we're sweeping under the rug right now. As the uncertainties get smaller and smaller, we're going to have to deal with those and have a good description of those. So I think that's a challenge, and I'll go ahead and finish there. Thank you.
So further, can you comment, for example, on how much, let's say, you said that one of the MPDF sets includes ion production from break? What is the effect on MPDFs? The reason for which I'm asking is because I have a concern. Ideally, an electron-ion collider would be the best place, arguably, to determine MPDFs. You can test whether it's really a fleeting twist nature, or we are fooling ourselves and we are throwing other effects into the mix. When you go to Brilliant, when they start to worry, E906 is measuring Brilliant in the region where supposedly MPDF's effects should be small, and the word on the street is they see modification, which may be related to in-medium radiative directions. It's kind of pretty consistent with what has been discussed for many years now in the literature. And finally, when we go to PA collisions, which I assume is included, you kind of have a mix of initial and final state effects, perhaps leading with MPDFs. So how can we differentiate?
Yeah, there's not a good way because we sort of lump them all together I mean, for example, in the pion case, we did take a look at different fragmentation functions, and there was a mild sensitivity there that we put into the errors. And again, it did have a pull. It did help out with gluon some, but again, the errors were quite large. I don't have any of those figures here from the paper, but we did have the issues of the fragmentation function that was an uncertainty, and we just assumed. Basically, we assumed we were sort of out of the higher twist region. So I guess you know that might be something to go back, and particularly as the error bars come down and look at. So we did not look at that.
Well, yeah. So this is about the comment about the question. You commented a little bit on the factors you were using that were depending on A. And maybe one of my questions is why do you use A as a scaling? Because especially when you're using things like helium or beryllium targets in the mix, we know that A dependence in the small a is not really relevant. Ideas or things to start using other things?
Yeah, so I showed you, sort of in the proton-neutron plane, we're sort of going down the stable axis there. And I guess, I mean, you could try using Z, but then what it means is as I pile on neutrons, more or less, then you would get the same PDF. And so A, in some sense, if you say the nuclear corrections are a collective effect from the more things you put there, A is what measures that. And if you have one variable you have to choose, A is what you choose. So I mean, maybe in the small A region, that's not so good. In the large region, it seems it seems like it might be better, particularly when you're trying to reach.
I understand, but okay, so what you're saying is one direction is to take into account the symmetry, and there's a lot of activity around that. I kind of agree with you that this is very difficult here because there is not so much data and that would have more things. But for example, instead of A, you could use binding energy. That's uniquely defined for every nuclei, like A, so it's as clean. At the same time, it varies much less, which is normal because binding energy actually is not so small, and it could be interesting to see the results if you could actually get a better K-square with some other things. Like there is nCTEQ, there are plenty of things that could be used there. I think the result to see if some of them work much better would be an interesting result. Just based on.
I confess it's not something we've considered, and again, I showed you behind the parameterizations how these vary. So some of them may be reconsidered.
That's at some level what Sergei and Roberto. They do that, isn't it? They essentially fold as virtuality. Essentially, they do kind of the binding. So there are other people who do that. So I think in the end we just have to compare. I mean, Fred. That's why I asked Fred to make this plot over Z over A, because in the end we're going to get calcium 40, 48, and then of course there are issues. But there are people who actually do exactly that. So,
yeah, no, I agree with you. But the thing is, it's interesting to compare them in the same framework, because when you have two different frameworks that have so many differences, it's very difficult to know if the difference comes from one of the modification or one of the many others in the calculation. While if you run exactly the same thing, just changing one thing, now you can really see the impact of this one thing.
And I mean, if you had data on that with different isotopes, that would be where you can really tell it. It's a little hard when you're going across it, but if you have something else,
it's just starting. So if I may, so thinking back to, or thinking forward to the IC, sorry. So in the white paper, right, we were thinking at small x, how do you tell what would be the signal for saturation, and among, of course, level 1 observables are structure functions and PDFs, nuclear PDFs. And the statement we converged on is, linear factorization approach doesn't predict the X dependence, you have to parameterize it, also doesn't give the A dependence, whereas iteration physics has specific predictions for both for X dependence and for A dependence if you take the ME initial conditions. So I guess it's a very sort of vague question. Can you, I mean, what's your feeling? So iteration physics can generate a specific prediction. Can you then fit it with a nuclear PDF? Is there sort of a limit of something that you would be able to describe? Or pretty much anything?
Yeah, that's vague. The challenge is right now there's a lot of play we can absorb into PDF. But actually coming back to the X-fitter, because on the proton side, there's been some renewed interest. Folks have looked at basically resumming splitting kernels. We heard a little bit about that before. And that seems to, one of the challenges was when you analyze here at next leading order, and then you go one higher order, the chi-square's got worse. What's going on? And if you use resum splitting kernels, there's some 1/x singularities that kind of spoil the next leading order stuff and make it poorly behaved. By resumming that, you got a better behavior. That actually is now built into X-fitter, so you can try that. And so one of the challenges, and that's open source, one of the things I would look for is if you're seeing something that might look like saturation for a small x, you might want to also go try this, try some of these resummations and see if those work. And if those work, then you have an explanation. If that doesn't do it, then you have to look for other explanations.
But EIC's strengths would be also A dependence, right? And those resummations, as far as I understand, say nothing about A dependence.
Yes.
And then the question is again, right? Can you pretty much?
Yeah. So then you have to look at the resummation dimension and then across A. Right. And I guess in principle you could do that. We don't have that in. We could put that in, but it would seem that would be the first place to look. And so in principle you can do that. That machinery isn't there. The proton machinery is next to it. But that would probably be the direction that we look at first.
Okay. Do you something else?
Yeah, it was just a comment, basically to echo Ivan's comment. Of course, the same holds for anything which is semi-inclusive. Similar concerns are for anything that's semi-inclusive, even given the massive scattering. And separately, just so that it's said once, the EPS09 fit did include pion data and overweighted it by a factor of 10. Just so that that is known. I mean, it's just not defendable in some sense. I mean, that has been removed as 16.
Include the semi-inclusive. The question is, what are you expecting to modify more? The transverse distributions or longitudinal distributions? Because then they will be kind of, to some extent, interconnected when you start to detect atoms. Okay. The question is whether, since we were discussing also the modified TNTs, how that is going to, or they are going to affect each other, or they can grow completely independent. What do you think?
Yeah, so we don't have a machinery in there, but so the comments more speculation. But coming back, as I said, on WZ, which is what we're looking at now, we're looking at rapidity. But as soon as we want to start looking at PT, that comes in because we can try to do a Collins-Soper-Sturman resumation, something like that. But if we can get some inside direction from some of the TNDs, that would be quite useful because that's always been sort of a challenge to get that, to get the small PT region. So I think that might be the direction we decided.
So one more thing, because Fred didn't bring them up, I think you showed only PDF sense for the quark, which is not always the most interesting one.
Mm-hmm.
But if you look at the gluons, there actually was very interested. EIC actually can make huge constraints, and we're starting to work on that to really constrain. Then EIC can really make a huge impact. If you look at the sensitivity plots, it starts looking like that. You really can constrain the gluons. Yeah, like a large action for not small action.
I should. Tim Hobbs was the one that did the
Yeah,
work
exactly,
on that, so he's been.
Yeah, it's not particularly interesting. All right, let's think that again. And we'll move to nuclear PDFs and GPDs, Salvatore Fazio.